Hi everyone, I am Alvaro Garcia Lopez. I belong to the Applied Physics Department in University Rey Juan Carlos in Madrid, Spain. I'm going to present the electrodynamic origin of the wave-particle duality. So in the first place, I would like to give some motivation to the present work, and one of these justifications came from the reading of David Bohm's seminal paper in 1952, A Suggested Interpretation of Quantum Theory in Terms of Hidden Variables. And I think this paper is very important because it contains the crucial ideas of chaos theory 20 years before the chaos theory was even named. Among many other things, in this paper, David Bohm says that quantum mechanics does not provide the mechanisms that explain quantum physical phenomena, because for that you need models, and quantum mechanics only has a statistical correspondence with reality, so there is only a statistical model. There is no a model in the sense of one-to-one correspondence with between mathematical models and reality. So in some sense, I like to say that quantum mechanics is like a calculator. Everybody knows learns how to use the calculator, but not many people, few people know why and how the calculator works. So I'm going to try in this work to obtain the wave-particle duality. I'm going to use a mechanism, nonlinear mechanism called self-oscillation. The second motivation for this work was the discovery by Yves Coudert in 2005 of walking droplets. If you have a fluid like a silicone oil fluid and you put it in a shaker and you force this fluid, you can take out a droplet out of the fluid with a toothpick. Then the droplet starts to bounce on the fluid. If the waves produced by the droplet has some slope, when the droplet hits the fluid, it can move horizontally. So the idea is that the droplet is creating waves in the medium, and these waves affect its at a later time the droplet. So all the past history of the droplet is affecting it at present time. So there is memory in the system through the wave mediated field. And this means that, contrary to Copenhagen's interpretation of quantum mechanics, which says that sometimes the particle is a particle, sometimes it's a wave, what you have is a pilot wave, as proposed by Louis de Broglie. So the idea is that the particle has a wave, is creating waves, and they are attached to the particle all along. So there is particle and wave at the same time. And finally, the third motivation in this view, one is a philosophical one, is that generally particles are considered points, Newtonian point masses in quantum mechanics. But on the other hand, it is also claimed that these particles without internal structure, they have internal properties. For example, internal angular momentum, as also called spin. So how is it possible that you have internal properties without having internal structure? So if, on the other hand, we assume that particles are extended objects, they can be active and they can self-interact electrodynamically, because the field perturbations produced by some part of an accelerated electrodynamic body travel in space-time and can affect some other part at a later time. So I like to use the metaphor of swimming rather than walking. So when you are swimming, you hit the water with one of your arms, you create a wave, and the waves affect you how you give the next stroke. So there is feedback in the system, and this creates self-forces. An extended object can self-interact, and this is described in terms of time-delay differential equations, which can produce Hopf bifurcation and nonlinear oscillations. So the mathematical framework I'm going to use is simply Maxwell's electrodynamics. No assumptions. This is very pure thing. So the Lagrangian density of Maxwell electrodynamics has two terms. One term for the fields with the Faraday form, and there is also a coupling between the fields in terms of the force potential and the force current density, the matter. Matter is just charge density and also current density, and these equations can be solved in terms of the Green's function, and you obtain the scalar and the vectorial potential in terms of the density of charge and current density, and importantly, you see here already the time delay. If you use a point particle, the solutions are very well known, and they are known as the Liénard-Bickert potentials. You can see them here, and I want to stress here the time delay, because if we have retarded potential, we must have retarded differential equations, and this is always missing in classical mechanics. So what's the model we are going to use for an extended particle? We will use two models. The first model is the simplest model you can think of an extended object, which is a particle. It was devised by David Griffiths in his book chapter 11, Introduction to Electrodynamics. And let's say you divide the charge into 2 points. They are at a fixed distance through a rigid charge density, and the distance of the the size of the particle, if you want, is d. This distance is not going to change. The entire particle has charge, the electron charge. So the idea is that if in some time had passed, if there is some, let's say you perturbate horizontally, transversally this particle, you would have some velocity, some acceleration, and because there is acceleration, you can create a perturbation of the field, and by one point, and the other point absorbs it at a later time. So the particle can talk to itself, listen to his voice from the past, and there is a self-interaction. You can compute, of course, the other point also can send signals to the first point. So you can compute the electric field created at the past acting on the present using the linear Beaker potentials, and it has a Coulombian part. It also depends on speed. This is speed renormalized by the speed of light, and there is also a radiation term depending on acceleration. So if you don't have acceleration, you don't have a radiation term, as it is well known. So, well, basically you can compute the net force exerted on the particle by itself, and the result using symmetry considerations, and also the fact that the magnetic part of the force cancels out for our arrangement. You can compute basically the self force of the particle itself. It has the Coulombian term and the acceleration term. So what should we do next? Well, what we are taught to do in high school, and we have done this many times in our lives as a physicist, is to apply Newton's second law of motion. So you would say the self force of the particle is mass, bare mass, mechanical mass, times acceleration. And if you do that, you can also Taylor expand delayed coordinates. This is done very frequently when the delay times are short, and you obtain a series, a time series, a Taylor series expansion depending on all the derivatives of acceleration, and the dynamical system will be retarded dynamical systems have infinite dimensions. But what I would like to stress that you can remake this series, and you will obtain a lot of non-linear contributions to all order, and also linear contributions, such as, for example, here the Abraham-Lorentz force, which is the back radiation force. But I want to stress this term because note that we get another term of inertia coming from the electrostatic energy. So energy, as claimed by Einstein, is mass, and electrostatic energy contributes to mass. So the total mass of the system would be the bare mechanical mass plus electrostatic energy divided by c squared. This is called usually renormalized mass. But I want you to think differently now. Change your mind. Forget what you were told in high school, and now think that there is no mechanical mass, because in the end macroscopic mechanics comes from microscopic electrodynamics, as a classical theory is more fundamental electrodynamics. So you only would have, if this hypothesis is true, only electromagnetic mass. So mass would be some emergent property, and it would be electrostatic energy divided c squared. If you do that, you can pose the equation of motion as a covariant equation as the sum of forces equals 0, external plus self force. And if you do that, you would get directly Newton's second law from electrodynamics, and it would be an emergent theory. So this already contains Newton's second law, and this has been called the D'Alembert's principle in historical terms. And if you use Arnold-Sommerfeld fine structure formula, you can even write mass. We will use this formula later on as proportional to h bar, which would explain why quantum mechanics and all terms containing inertia appear proportional to h bar, as for example angular momentum. So we want to solve the free particle, and because there are no external forces, our dynamical equation would be self force equal to 0. And if you do this, you obtain nonlinear and nonlinear oscillator, very similar to Lord Rayleigh's nonlinear self-oscillator appearing in his book The Theory of Sound, to study the vibrations of a clarinet reed. I have advanced the equation because all the time here should be retarded, so I advanced it, and now we have an advanced differential equation, but it is a kind of particular kind of delayed differential equation. You have the inertia term. This is the dissipation, very similar to Lord Rayleigh's oscillator. This comes from the Lorentz gamma factor. You have here the Hooke term and a nonlinear term multiplying, and you have the non-conservative part of the equation here appearing as an advanced term. And the good thing is that if you do some tough mathematical computations, all exact analytical computations, you can show that the time delay depends on the acceleration of the particle and the speed of the particle. So this means that the particle is going really fast, and it's accelerating. The self signals, the voice it hears from itself, comes from earlier times in the past. And this is a very important thing, because usually time delay is considered constant, but here we have to insist that they depend on the dynamical motion. So there is very complicated feedback. All the computations can be found in this paper, published in 2020. And what we did here in this paper is just to study a stability analysis. You compute the characteristical polynomial of the rest state, or any uniform motion of the particle, and this is the characteristical polynomial you obtain, and you can compute the eigenvalues of this polynomial. And here you see the domain coloring representation. The black dots where all colors meet are the eigenvalues. There are an infinite number of eigenvalues because you have time delay. You see that they have real part and also an imaginary part. The real part is positive. That means the uniform motion is destabilized. So you put the particle if you want at rest, you perturbate it very little, and and you get a frequency. The frequency is really high. It's 10 to 21 Earth. That's called there is a similar frequency appearing in the Dirac's equation. It's called Zitterbewegung, the trembling motion of the electron in quantum mechanics. But here we show that it's also present in classical theories, and it explains that the particle has a wave. It is trembling all the time. And this is a kind of oscillation, or linear oscillation, called self-oscillation. We have done the same thing with a spherical particle, and you see, we observe that the longitudinal motion is dissipative, so you get a Hopf bifurcation, and all the eigenvalues have now negative real parts. This is a characteristic polynomial. And well, what we have found is that the stability of the particle depends on the shape. But if you put now we are working, we put some external field fluctuations, 0-point fluctuations, or if you want, you can put constant electric field, and the particle starts to, it does the Hopf bifurcation already. So finally, to conclude this presentation, you can compute the self-energy of the particle. That is the energy, the electromagnetic energy of the particle, given by the non-solenoidal part of the fields, the conservative part, if you want, in some sense. And what we obtain using a lot of mathematics, you can check that in the paper, using the electromagnetic mass, which is very important to obtain these equations. You obtain first from electrodynamic origin purely Einstein's mass energy relation with the gamma factor. So this says that we are doing things right. And there is another new thing that has been found, and it can be written here as this. This I call the quantum potential, because if you look at this, h squared divided 2m appears in the Schrödinger equation, and Bohm's formulation, David Bohm's Bohmian mechanics, transforms Schrödinger equation using polar form of the wave function to show that it's a Hamilton-Jacobi equation with a new potential, non-conservative potential, which is the quantum potential. And you see that you have here the acceleration, and it's even time retarded, that it depends on speed. Just to give an approximation of this quantum potential to understand how the stability, you lose the stability, you can use the harmonic oscillator formula. Acceleration equals minus the frequency squared by possession, and then you develop in series, and the two first terms in the expansion give you just a Duffin potential. So basically the rest state, you see it here, is destabilized, and the particle starts to jiggle. And this constitutes a phenomenon of symmetry breaking, as that one found by Phil Anderson in the Higgs mechanism, for instance, but it's a symmetry breaking of the Lorentz group, triggering a nonlinear oscillation. The main conclusion of this work is that Newton's laws only hold on average. So all theories which are mechanical, using as a basis Newtonian symplectic structures, as quantum mechanics and both the Schrödinger and the Dirac equation, cannot be fundamental, because Newton's laws are not fundamental in themselves. We have to take into account time delays and retardations. That's it. Thank you very much. I hope you have enjoyed, and I will answer